Hello. In part 1 of Cholesky Factorization tutorial, I showed you how the decomposition algorithm is derived and applied to get a lower triangular matrix. In this video, I will show you how to use the lower matrix to solve a system of linear equations by using the forward and backward substitution. So let's start. The main goal of the LU decomposition methods like Cholesky factorization is to transform the coefficient matrix of a given system to lower and upper triangular matrices in such a way that makes the system easy to be solved by substitution. That's why we can divide the solution procedure of a system by using the LU decomposition method to two stages. The first is the decomposition of a matrix of the coefficients to upper and lower triangular matrices. Then we can substitute them in the system as shown here. So we have the lower matrix and the upper matrix in addition to the vector of the knowns x and the constant terms vector b. The problem may look more complicated now, but what we do here is to divide the system into two linear subsystems. We take the upper matrix and the x vector together and call their product vector y. And by substituting y in the lower matrix equation with the constant terms vector b, we obtained a second subsystem. For this arrangement, we have a two-step solution. Since b is known, this system of the lower matrix should be solved first to get y. And because the coefficients matrix here is lower triangular, that can be done by the forward substitution. In the second step, by using y as the constant terms vector of the upper matrix system, it can be solved for x by backward substitution in the same way in Gauss elimination method, which I explained in details in a previous video in this channel. The forward substitution is used to solve the system when the coefficient matrix is lower triangular, as we see here. It is called forward because the substitution procedure starts at the first row, where there is only one element, L11, then goes down to the last row, n. The set of linear equations are obtained simply by matrix multiplication. Then the equations are rearranged to find the unknowns, which are here the elements of the y vector. For example, the value of y1 can be found from the row 1. y2 is calculated by substituting the value of y1 multiplied by its coefficients in the second row. And the same procedure continues to the last row. By observing the indices of the elements in each step, we can write the general algorithm. Notice that the summation value does not exist if I is equal to 1. So we get the correct value for y1. The backward or back substitution applied to the system with the upper triangular matrix of coefficients. So the calculations go backwards from the last row where the element u and n to the first row. At the end, the elements of x vector will be found. As mentioned before, the constant terms vector here is the y vector, which calculated by forward substitution. For example, xn is equal to yn over u and n. The x in the upper row, x sub n minus 1, is calculated by using xn. The substitutions continue up to the first row. Therefore, the algorithm can be written as the loop of I goes from the last element to the first. In the code, a negative step value should be defined for this I loop. However, the summation loop of j can proceed normally from I plus 1 to n. In this tutorial, the backward and forward substitution techniques are applied with Cholesky factorization. But keep in mind, the same techniques can be applied with all other LU decomposition methods as well. In this example, the system having a symmetric matrix of coefficients is to be solved by using Cholesky factorization methods. So let's go to our editor. I will start the code by adding the forward-backward substitution function to the Cholesky factorization function developed in part 1. So let's first define the function. Let's call it solve LU. And it will take 3 arguments: the lower matrix, the upper matrix, and the constant terms vector. Now, let's define these matrices and the vector as NumPy arrays. Now, let's get the size of these matrices. So, now, according to the size, let's define the 2 unknown vectors. Now, let's begin the loop of the forward substitution. So the range here is from the first row, which has index 0 in Python, to the last row, n-1. But because, again, we know that range function will not approach to n, it will stop at n-1. So in this way, we completed the algorithm of the forward substitution, and we start the backward substitution. Let's explain this loop. We start at n-1, which is the lower row. Actually, the problem here is this. As we know, if we put 0 here, so the loop will go up to the second row. So we should say -1 here in order to guarantee that the row which has index 0 is taken into consideration. Finally, the step size should be negative because this loop is descending loop. It's not ascending, it's descending, so it starts from large value to smaller value. Now, let's continue. Finally, we return the value of the solution x. So these are the coefficient matrix and the constant terms vector of this system. Now let's go and apply the solution. The solution will be in 2 steps. First, we need to get the lower matrix by applying Cholesky factorization to A. Then we want to get the solution, let's call it x, equals to the solver or solve LU, and of course the lower matrix is L. The upper matrix is the transpose of the lower matrix. So in solution of the Cholesky factorization, as we discussed in the part 1, the upper matrix is simply the transpose of the lower matrix. Then the B vector. Now let's print X and let's try to run this code. So as you see here, we obtained this solution of the system. We can use NumPy's linear algebra solver. So we can say here X, or let's directly print A and B, and let's run the code again. So as you see here, the both solutions actually are identical because we have the correct solution by using Cholesky Factorization and backward-forward substitution. So in this way, we verified our solution by another solver from NumPy. Now, before ending this tutorial, let's reduce the size of the code at forward and backward substitutions by using the slicing of NumPy arrays. So the slicing technique will reduce the size of this code just by getting rid of the J loops and J summation. So let's start it. So at the beginning, we remove everything related to J loop. Also sum J, and we replace it now we add the summation routine of NumPy. In this way, and also this loop goes from 0 to I, so we'll go so in this way we guarantee that the system or the internal loop will go as we need according to the algorithm. Now let's do the same thing in the backward substitution routine. And this way we reduce the size of the code by using some NumPy summation and the slicing technique with the same limits or of the loops of J in both cases. Now let's run the code and see the result. Okay, let's see here. What's the problem? Oh yeah, I made a mistake here. It should be I plus 1. Okay, let's run the code. And it works exactly as we tested before. So in this way, we completed the part of the solution. Again, we should not forget that this routine of solution of forward and backward substitutions can be applied for all other LU decomposition methods as well as Cholesky's method. If you like this video, please hit the like button, and to be notified for the coming videos, subscribe and hit the bell. Thank you for watching.